The final topic that we're going to talk about in logic combines some of what we've done before and builds on it. So we're going to talk about quantified statements today. So sometimes we can take an open sentence and then we can convert it into a statement itself through this method called quantification. So what we do when we do this is we add some kind of phrase into the front of the open sentence. So if I had an open sentence, P of X, then I add to it the phrase, for every X in S, with S being the domain of P of X, then what I'm doing is I'm making what's called a quantified statement. So when I add the phrase for every element in a set, what I'm using is called the Universal Quantifier. Universal because it's every, it's all. So whenever we hear this, we should be thinking about every single element in the set, universal, across the board. So you see for every, Universal Quantifier, all of the things, all right? And whenever we write this, it's like an upside down A for all right? Yeah, A for all, yeah, all right. So I've already used some of the alternate phrases that we use instead of for every. We use for each and for all. I tend to lean towards using for all just because it helps me remember that upside down A. And yeah, but all three equally correct. Take your pick, whatever you like the best. Just be able to recognize it in all of those ways. So there's two statements here, and one of them is using the symbols. Statement 1 has that upside down A with the X in S, and then our open sentence P of X. All right, and we can use words to say it instead of using symbols, and we would say for every X in the set S, P of X. All right, so this statement is true only when P of X is true for every single element in the set. If it's false for just one element in S, then this whole statement is false. So there's a second way that we can quantify a statement, and it's using a thing called the existential quantifier. Don't let that big word throw you off, all right? Existential, there exists, all right? Existential exists, yeah, all right. So we've actually already kind of hinted at this when we were thinking about when the universal statement was false. It was just, there just had to be one element in the set that it didn't work for. In this case, here we are with the existential quantifier. What this is saying is there's at least one element, there's some element in the set that this is true for. So the existential quantifier, we use a backwards E for existential or exists, all right? So lots of phrases we can use here. There exists, there is, for some, for at least one. Take your pick. Again, I tend to say there exists a lot to help me remember backwards E for my symbol. So here again, I have the quantified statement written two ways, one with the symbol, that backwards E, and the second way out in words with there exists, X in S, such that P of X. So this statement's true as long as there is one, at least one. There can be more than one, but at least one element in S such that P of X is true. If there are no elements in S that make P of X true, then the existential quantifier, that quantified statement, is false. So here's an example of an open sentence over a domain that we're going to turn into a quantified statement two different ways. We're going to use the universal quantifier, and then we'll use the existential quantifier. So for the universal quantifier, what we do is we say for all n in S, our domain, P of n. So that means that for every single number 1 through 7, that's all of our elements in S, then 2n squared plus 5 plus negative 1 to the n, all divided by 2, is a prime number. So if we go through and we start checking, this works for several of the values, and we get to P of 5. And when we plug P of 5 in, we get 5 squared is 25. We get 50 plus 5, 55. And then we take -1 to the 5th, and that gives us -1. So we have 55 minus 1. So we have 54 divided by 2, which gives us 27. And we know that 27 is 3 times 9. So 27 is not prime. So that makes this quantified statement with the universal quantifier a false statement, because we have one example that breaks it. Now, if we instead use the existential quantifier, what this is saying is there exists some value in my domain such that this statement is true. So I plug in a value from my domain. If I plug in 1, I get 2 times 1 squared is 2, plus 5 is 7, plus -1 to the first power, so that's -1. So I have 2 plus 5, 7, minus 1, so I'm 6 divided by 2, so I get 3. 3 is a prime number, so this is true. So this is a true statement with the existential quantifier, because there is a value, at least one value, in my domain S that makes it a true statement. So let's consider a different open sentence. So let's consider Q of x, an open sentence that says x squared is less than or equal to 0. Now, if we put the universal quantifier out in front and say, for all x in the real numbers, Q of x. So what I'm saying is, for every real number x, we have x squared is less than or equal to 0. You're probably thinking already, that's not true, because 1 squared is 1, which is not less than or equal to 0, so it's false. Notice that that makes this statement false, which means the negation is true. So the negation of the universal quantifier is saying for every real number, x, we have x squared is less than or equal to 0. Now remember, to show that it's false, we just need one that it's not true for. So really, the negation of this is saying there exists at least one that it's the opposite. So we really have the negation of this is there exists some real number x such that x squared is greater than 0. Notice what I've done is I've gone from having the universal quantifier to the existential quantifier. Whenever we negate a quantified statement, we switch between the two quantified statements. So here we have the negation of that universal quantifier statement written out with our existential quantifier notation. So when we bring this all together, what we've found is that when we have the negation of our universally quantified statement that we got from some domain and open sentence, what we really have is the existentially quantified statement over the same domain, but with the negation of the open sentence. So let's look at an example with an existential quantifier. So there exists a real number x such that x squared equals 3. So we have this open sentence, P of x, that says x squared equals 3. So we can rewrite this with notation that the real numbers are our domain. We have the existential quantifier within that domain, and then we have our open sentence. So this statement is going to be true since when we plug in the square root of 3 for x, it works, or negative square root of 3. But if we take the negation of this, whenever we negate an existential quantifier, it becomes the universal quantifier. And again, then the open sentence that we had is the negative of that. So the negation of there exists a real number x such that x squared equals 3 is for every real number x, x squared is not equal to 3. So that statement's going to be false because we have an example of when x squared is in fact 3 and x is a real number. So here we have another example of negating a universally quantified statement. So if we have the universally quantified statement for all integers a and b. A and b are in the integers. There we go. We have our domain, all right? And we're looking at all of them, all right? Universally quantified. Then the next part is going to be our open sentence. So our open sentence says, if a times b is even, then a is even and b is even. All right, so there's some complicated logic happening in there. We have an implication and a conjunction. All right, then we go through and we're going to negate that. So remember, when we negate a universally quantified statement, we're going to create an existentially quantified statement. So we're going to use the there exists, and again, we have the same domain, same variables. So integers a and b in the integers, right? And then we have our open sentence, but we have to negate it. So we're going to negate our open sentence from before. So negating that implication with a conjunction ends up giving us a conjunction with a disjunction. All right, so we're going to have a times b is still even. All right, so we have this part matching up here, right? And then instead of having an implication, we have our conjunction, and taking our conjunction here that we had before in our implication, we make it a disjunction because we're negating it. So it's going to be an or, so we have a or b is odd, because odd is the opposite of even, right? So that's negation of it. So our universally quantified statement of for all integers a and b, if a times b is even, then a is even and b is even, actually becomes there exists integers a and b such that a times b is even and a or b is odd. And here we see the negation is true, the original statement is in fact false. Here we have an example where we're going to negate an existentially quantified statement. So I have two sets, A and B. So we're going to have our original statement, our existentially quantified statement. We're looking at a rational number R, so there's our domain, rational numbers. All right, and our open sentence is that R is in A or R is in B. So we can look at A and B and we know that that's in fact a false statement. So the negation is going to be a true statement. So the negation of an existentially quantified statement, we're going to be creating a universally quantified statement. So we take our universal quantifier for every, we keep our domain the same, rational numbers, and then we're going to negate the open sentence. So our open sentence before was R is in A or R is in B. So that was a disjunction. And remember, when we negate disjunctions, they become conjunctions with the opposites, with the negatives, all right, the negations. So the negation of R is in A or R is in B is R is not in A and R is not in B. So there we have our universally quantified statement that is the negation. For every rational number R, both R is not in A and R is not in B. Another thing we can do with quantified statements is we can combine quantifiers in different orders and make more complicated statements. So consider an open sentence P of X, Y. We've got two variables here. So the open sentence is going to say X plus Y is prime. So the domain for X is going to be my set that has the numbers 2 and 3 in it. And the domain for Y is going to be a set T that has the numbers 3 and 4 in it. So whenever we have multiple variables, they can come from different domains. We need a domain actually for each variable. So we're going to make a quantified statement here. So this quantified statement is going to say, for all X in S, there exists Y in T such that P of X, Y. So every single variable can have a different quantifier on it. So I could have had for all x and for all y. I could have had exists x for all y. I could have the pairing that I have. I could have exists and exists, all right? So they get paired up however we want, all right? But we're going to look at for all x, there exists y, p of x. So to write this out in words, we would say for every x in S, there exists y in T, such that x plus y is prime. So what we have to do is we have to look at every single possible x value and make sure that one of the possible y values works, that when we do the sum, we get a prime number. So the first x value I need to consider is 2. So I need 2 plus 3 or 2 plus 4 to be a prime number for this to be true for 2. So I notice that if I take 2 and I add 3 to it, I get 5, which is prime. So this works for 2. And now I need to move on to the next x value, because you have to do this for all x values. It doesn't have to work for all of the y values, just for all of the x values. So my next x value is 3. So now if I take 3 plus 3, that's 6, doesn't work. And then I could try 3 plus 4, and I get 7. It does work. And so I end up with this working for 3. So since this works for both values in the domain for x, all right, that means that for every x in S, there is a y in T such that x plus y is prime, so the statement is true. So now let's switch up where we have the quantifiers and what the quantifiers are. So I'm actually going to keep the quantifiers paired up with the variables the same way, but we're going to change the order that they read in. So when we say this in words, it's going to say there exists some y in T such that x plus y is prime for every x in S. All right? So what this is saying is there's some y that when I pair all of the values of x with it, then x plus y is going to be prime. So I need to check my different y values and see if this works for any of them. So I take 3, it's one of my y values, and I add 2 to it. That's prime. That's good. But it has to be for every x in S, so I also have to do 3 plus 3, which is not prime. So that one doesn't work. So that 3 for a value for y is out. It's not going to be the one that exists that this works for. So we're going to try 4. We're going to try another value for our y. So we take 4 and we add 2 to it. We get 6. So this doesn't work because it's not prime. So there does not exist some y in T that makes this work, which makes the statement false. So this chapter had a lot of symbols for us. Just kind of keep this symbol bank going. If I were you, I would probably be making a list of the symbols and putting it somewhere, and make sure that you're comfortable seeing them and you're getting fluent with them, and hopefully are fluent with them by the time we're taking an exam with them. So our final topic is characterizations. No more symbols introduced here, just a concept, all right? So if we have some mathematical object that we can describe in a certain way, like in a definition form, but there's another way that we can describe it. So say our definitions usually actually are in the form of open sentences, right? And there's some other open sentence that we can use to describe the object as well, such that the biconditional between the two open sentences over some domain, that's the same domain for each, is a true statement. Then the statement that's not the definition is called a characterization of the concept. So an example of this is irrational numbers. We'll be using the definition of irrational numbers a decent amount, where they are real numbers that are not rational. But sometimes it's helpful to think about them in a different way. So one of the ways that we think about them is as real numbers whose decimal expansions are non-repeating. This gives us a characterization of an irrational number. So we can write this as a real number r is irrational if and only if r has a non-repeating decimal expansion. And it should be noted here, this non-repeating includes the zeros that go on forever at the end of a terminating decimal. Right? So another example here, equilateral triangles are defined as triangles whose sides are equal. That's what equilateral is always meant for us. But sometimes we need to think about them in terms of something other than the sides, and it's easier to think about the angles. So we can characterize an equilateral triangle as one whose angles are equal. So we have a triangle T is equilateral if and only if T has 3 equal angles. This biconditional is true, and so it is a characterization. So it's important to note that if the open sentence is the definition, it's not a characterization. However, if it's something that's like an alternative definition, then it's in fact a characterization. And we'll use characterizations very regularly when we're proving things. We'll want to think about things coming from different directions, and it's really easy to think about alternative definitions, which are characterizations.